Hi, I'm Fernando Pereira from the Federal University of Minas Gerais in Brazil. And today we continue to see how we can use machine learning techniques to predict properties of programs. In the last video, we saw examples of applications of machine learning in the auto-tuning of compilers. Now I will define a branch of compiler research called Predictive Compilation. In the last class, we saw that John Cavazos designed techniques to choose the best optimization to compile a particular Java method. He published some of these findings in his paper, Hybrid Optimizations, which optimization algorithm to use. That was in 2006. Key to determine the best optimization or the best sequence of optimizations for a certain method is the ability to predict the improvement of different optimizations. So, can you think about different ways to predict the improvement of an optimization over a program? If you want, you can stop the video right now and think a bit about it, because then I will give you a few answers. To make things more concrete, let's try to reason about code size. Code size is a metric that does not vary. Speed varies a bit, You can measure the same program twice and then get two different results. Size, in turn, is a discrete number. We measure it and we have it. Variance is zero. But how do we measure code size? Think about it. How would you measure the size of a program? Well, this question can be rephrased like this. What is actually code size? How do you specify the size of a program? We can let size be the number of LLVM instructions in a program, for instance. To get this number, just compile a program to produce code in the LLVM intermediate representation, and then use the instacount pass from OPT to get the number of instructions. The number of LLVM instructions is given at the end of the statistics that instacount prints. Another option is to measure the size of the executable. In this case, we can simply count the number of bytes in the executable binary, for instance. But anyways, there are lots of ways to define the size of a program. The important thing is to be consistent. And notice that in this case, when considering code size, we can be sure that we are dealing with a metric that does not vary. The size of a program is always the same, given a certain way to produce that program, of course. So let's return to our problem of predicting the impact of compiler optimizations on the size of programs. Imagine, for instance, the impact of Clang -OZ, which is one of the optimization levels that's tuned for size in LLVM. This is a sequence of many optimizations. What's the expected code size reduction that we get by compiling a program with -OZ? Or rather, if we look into a program, can you try to predict the expected reduction? If you want to find out the answer, the average reduction that we get from Clang -OZ, you can check out this paper, Exploring the Space of Optimization Sequences for Code Size Reduction Insights and Tools. But the simplest thing that we can do to predict the average improvement of some sequence of optimizations in code is to compile many programs with that sequence of optimizations. That will give us some idea of mean and median improvement. In this paper from 2021, the authors compiled thousands and thousands of programs to get this average. For instance, let's take some programs. You can get lots of them from Bench. There are 1 million compilable programs in this repository. If you want to know how they were collected and curated, you can read the CGO paper from Silva et al. But anyway, can you guess the average reduction that we obtain if we compile a program with Clang -OZ? I'm going to help you. It's a number between 0 and 12. Perhaps on the average, programs after -OZ are, 12 times smaller. Well, but that's maybe too much, right? The median reduction is of about twice. And the mean reduction is of about 2.47 times. Well, when using those programs from Bench. That's pretty much also what we get in terms of speed up. So in the end, if anyone asks you what's the average reduction that we should expect when compiling a program with Clang -OZ, you can say, well, maybe 2.5. Notice that we are measuring the number of instructions in the LLVM-IR. Anyway, if you need to predict the impact of optimizations on programs, you can simply use these averages, and then you are done. Or are you not done yet? What would be the problem with this approach? I mean, we need to predict the improvement of some optimization, then we get lots of data and we average the improvement of those programs, and assume that this is the improvement in general. What's the problem? Well, one of the problems is that the data may not really be normal, and then we will have problems with outliers. And, well, another problem is that we are treating all the programs in the same way. But ideally, we would like to treat programs differently. Some programs can be better optimized by some sequence of optimizations that's not necessarily the same for all the programs. This ability to treat each program in a particular way is called predictive compilation. Predictive compilation is today a whole area within programming languages that was pretty much started by the work of John Cavazos, and also by Michael O'Boyle from the University of Edinburgh, who trained many students in the subject. Counting also Gregory Fursing, they actually even worked together on the design and implementation of predictive compilers. Most of the foundations of predictive compilation was defined by the work of those gentlemen. And so, going back to the problem of predicting the best optimizations for some program, we want to treat different programs differently. I mean, perhaps the best sequence of optimizations for program PA is not the same as for program PB. And we need to associate each program with a good sequence of optimizations out of a large set of candidate sequences. So, we want to design a mechanism to predict the benefit of different sequences of optimizations on programs, but we don't want them to deliver always the same average for all the programs. The same sequences, if applied onto different programs, are allowed to give different results. In short, we want a technique that's flexible and predicts for each program the best sequence of optimizations for that specific program. In this way, we can conclude that program PA should be optimized by a sequence that's not the same as the best sequence for program PB. This process of predictive compilation consists of three parts. First, we collect data to help us to understand the behavior of programs. Then, we use this data to train a model that will be able to infer the property of interest to programs that we have not seen before. And then, we use this model to predict the properties of other programs. So, if we have a program PU, we can check among the programs that we know from training which one is the closest to PU. Maybe that's PA, the program that's the closest to PU. And for PA, we know that we need to optimize it with the sequence of optimizations that's called SAC3, whatever that is. And that's how we will optimize PU. Perhaps that's not the best sequence. Remember that approximations are acceptable, but we hope to build models that are accurate enough so that we can be right or close to right as often as possible. But anyway, how to do this kind of prediction concretely is something that we will explore in the next class.